All right, baby shotties, welcome back. Today we are going to talk about 7.4, which is going to elaborate a little bit more on what we did last section on parallelograms, but what we are going to talk about today, sorry if you can hear, I'm just filling up some coffee here, but we're going to look at special types of parallelograms. So, whole chapter we're focusing on is quadrilaterals, which are four-sided objects. Parallelograms were special four-sided objects or quadrilaterals where the opposite sides of that shape were parallel to each other. And we talked about some of the properties of how the opposite sides and opposite angles were equal. So what we're going to talk about today are actually some special types of parallelograms, things you might have heard before. So first thing we're going to look at is one special type of parallelogram, which is called a rhombus. So a rhombus is going to be a parallelogram where, again, we have the opposite sides being parallel, but the key thing here is that the opposite sides are going to be congruent to each other. And in this case, we're going to look at all four sides being congruent. So on this diagram, a rhombus, we have A to B. That side would be equal to B to C, would be equal to C to D, that all of these lengths would be the same. So for an example, if this was 10, that means all of the lengths would be 10 units long. Very similar to a square, but the only difference here is that a rhombus, you're not going to have those 90-degree angles here. So all the sides are going to be equal. So what we're going to talk about, so we're going to focus on some special properties of rhombuses or rhombi. We talked last time about parallelograms and the whole idea of diagonals and the angles within them. So we're going to look at the diagonals of a rhombus and the angles of a rhombus. So the diagonals, again, diagonals are lines that connect opposite points or opposite vertices of this shape. So a diagonal would be A to C shown there in the blue line and D to B in the blue line. So this is actually something we looked at in chapter 6. But when I draw those two diagonals, what ends up happening is that those diagonals are going to be perpendicular bisectors to each other. What that fancy jargon means is that when we find that middle point right here, that it's going to essentially cut each of these diagonals into equal parts. It's going to bisect each other. And then the other sassy thing is that when they bisect each other, that they're going to do that at a 90-degree angle. So again, that idea of perpendicular means 90 degrees. So the diagonals are going to cut each other in half at a 90-degree angle. And then in terms of the angles of a rhombus, so not only is it going to cut the diagonals in half, but we also are going to see that the diagonals are going to cut the angles in half. So the diagonals of this rhombus are going to serve as bisectors. So I'll just give you an example here. If I were to look at angle D, notice that I have that blue line there, so I'll just kind of sketch it down here. So that diagonal, which is the blue line, what it's going to do is it's going to cut this larger angle into two equal parts. So I would have a part there and a part there, that those two angles would be equal in magnitude. So let's say, for example, this was a 30-degree angle. That means each of these smaller chunks would be 15. So we're going to use this idea of diagonals and the angles of a rhombus to try and solve for some unknowns. So our first example here, we're going to use actually the diagonals of a rhombus. So you have the rhombus here, A, B, C, and D. You are given the diagonals. They intersect at point M, and we'll say that point M is going to be right here in the middle. Okay, so we'll call that point M. Tells you here that A to M is going to be 2x minus 10, and M to C is negative 3x plus 20, and I want to find the lengths of the diagonal AC. So you are given A to M, which is that small chunk, and M to C, which is that small chunk. So here's the idea, is that the diagonals are going to bisect each other, meaning A to M is going to equal M to C. So what I'm going to do to try and figure out the length is I am going to take the 2x minus 10, which is A to M, and I'm going to set it equal to 3x or negative 3x plus 20, and that is MC. And my goal then is I'm going to try and solve for x. So to solve then, again, that line down the middle, I would add 3x to both sides to try and gather my x's together. That would cancel, give me 5x. At the same time, I'm going to add 10 to both sides. Again, cancel here, and that would give me 30. And then if I solve for x by lastly dividing both sides by 5, I would get x equals 6. So if x is equal to 6, what I want to do is plug that in to those lengths. So if I were to just plug it into the 2x minus 10, I'll do 2 times 6 minus 10, which would give me 2. And if I were to plug it into the other one, I'll do it here in red so you can see. If I were to do negative 3 times 6 plus 20, what I would also get is 2. So that means the length here would be 2, and the total length would be 4. All right, so B, we're going to do a very similar example. Again, we're going to try and solve for the diagonals of a rhombus using the fact that they bisect each other. So very similar problem here. You are given length AC. So A to C is the total segment. Okay, A to C would be the total segment that you're given. And then you are given M to C. Again, M is going to be that midpoint. So you're going to give that smaller piece right here. Okay? And our goal is to find the lengths of AC and MC. Now, here's the only difference about this problem compared to the last one is notice I'm giving you the full diagonal and I'm giving you the smaller piece. So here's what we know is we know that this diagonal is being bisected, which means that the two smaller pieces are equal to each other. So if I give you one of the smaller pieces, MC, and we want to try and figure out how does that compare to AC, what we need to know is that when I have MC, which is 2x plus 28, that if I want to compare that to the total segment, I need to take that and double it. Okay, being cut in half means that if I were to double it, that would give me the full length. So if I were to double that segment, that should equal A to C, which is 8x plus 12. All right, so by doubling the segment, again, I'm going to have to double each of those numbers. I would then have 4x plus 56, and that's going to equal 8x plus 12, and then my goal would be to solve for x. So again, to solve, I would just subtract the 4x from both sides. That would get it cancel. I would then subtract the 12 from that side, bring it over there. I know I'm doing two things at once, but I'd get 4x left over on the right side, and then 56 minus 12, which would give me 44. And then lastly, divide both sides by 4, and I know that x is going to equal 11. Okay, so now if I were to plug that in, I will then be able to find the lengths. So if I were to do, for example, for AC and do 8 times 11 plus 12, which would give me 100, and then M to C, which is 2 times 11 plus 28, that, oopsie, I wrote 88, not 28, folks. Holy strawberries. So plus 28, that should give me 50. And notice, again, this is what we're saying, that if it's cut in half, bisected, that notice the smaller piece, MC, is half of the larger one, which is 100. Okay, so what we did here is use that idea of diagonals, bisecting each other to try and solve. So similar types of problems. These are a little bit more difficult because obviously our diagrams are getting a little bit more involved. All right, next question here, we're going to get super sassy. So now we're going to look at the angles within a rhombus. So the idea is that the diagonals, which are the blue lines shown here in the rhombus, bisect every angle, meaning that each angle here, A through D, is going to be bisected. So our goal is to use the ideas that we know about rhombuses and possibly parallelograms to try and solve for unknown angles. Okay, so try and follow me here, because what we're given is we're given one angle, in this case 61 degrees, and that is this tiny angle right here. What I want to know then is, based on that one angle, can we find angles 1 through 4? Okay, so here's what I know. I know that in a rhombus, the blue lines, called the diagonals, bisect each angle. That means if this angle is 61 degrees, then the angle next to it also must be the same, which is going to be, in this case, 61 degrees. Now, that is not one of the angles I'm trying to solve for, but that information is helpful because here's what we learned. A rhombus is a special type of parallelogram, and in a parallelogram, the opposite angles are always congruent. So if this angle is 61, the angle across from it, or opposite to it, is also going to be that same measure. So we know that angle 3 here is also going to be 61 degrees. The same time, the angle across from this 61 degrees, which would be angle 2, must also be the same measure. So I know that that angle will be 61 degrees. So right away, I know that angle 2, I'll just write over here, angle 2 equals 61 degrees, angle 3 equals 61 degrees. Okay? Now then I have to find angles 1 and 4. Okay, so what we also know is that in a rhombus, the diagonals that set are perpendicular bisectors, which means they are going to cut those diagonals into equal parts. Now that's in terms of the side, but when they bisect each other, they do so at a 90-degree angle, which means that at the intersection of those two diagonals, you are always going to have a 90-degree angle, which means then that angle 1 has to be 90 degrees. Okay, so this is going to be 90 degrees. Now, that leaves me then to find angle 4. Now, angle 4, this one we're going to have to use some other properties. What we learned about in section 1 is that notice when I have all my diagonals of a rhombus, do you see how it creates a small triangle within here? Okay, notice that angle 1, angle 3, and angle 4 are the three angles inside of that triangle, and here's what we learned about. That in a triangle, if I were to add up angle 1 plus angle 3 plus angle 4, they should all add up to 180 degrees. So if I know that 1 is 90 and I know that 3 is 61, I want to know what angle measure would I have there to give me 180 degrees. So by doing some algebra there, I know then that this angle must be 29 degrees. Okay, so angle 4 would have to be 29. So using all of these properties we've learned in the first 3 sections here, we're using these to try and solve for some unknowns. All right, so let's take a look at example B. Now B, we're going to use the same kind of idea with the rhombus. This one's a little bit less involved, but we're going to see if you guys can figure this one out, all right? So again, what we do know is that the diagonal of a rhombus is going to bisect the angles. Now notice here I only give you one of the diagonals, but here's the idea. These are being bisected. So that means angle 1 and angle 2 are going to be the same, okay? Now, if angle 1 and angle 2 are the same, based on a rhombus being a parallelogram, we know that opposite angles are always going to be the same. So if angle 2, whatever it's equal to, should also equal angle 4, and angle 1 should also equal angle 3. So again, these are opposite angles, and in a parallelogram, opposite angles are always going to be congruent. So the idea is this, is that angle 1 is going to equal angle 2, is going to equal angle 3, is going to equal, whoopsie daisies, is going to equal angle 4. So all 4 of those angles are going to be the same measure. We just got to figure out what that is and how we do it. Now to do this, let's use kind of what we did in the last problem. Notice here that I have a triangle, okay? And that you are given one of the angles. And here's the idea again, is that if I were to take angle G plus angle D plus angle F, and when I talk about D and F, I'm looking at these smaller angles. They should all add up to 180 degrees. So if I know that this is 118, I got to know what 2 angles would give me 180 degrees. The idea is, though, is that these 2 angles are both the same. So here's what we're going to do. We're going to take 180 degrees and we're going to subtract 118 degrees, which would give us 62 degrees. Now, because we have 2 angles, angle 1 and angle 3, that are both the same, that 62 degrees needs to be split up into 2 parts. So I'm going to divide it by 2 and get 31 degrees. So that means angle 1 and angle 3 are both going to be 31 degrees, which means then that angle 2 and angle 4 must also be 31 degrees. Okay? So if I were to fill this out, this would be 31, this would be 31, this would be 31, this would be 31, and heck, this one would be 118 as well. Okay? Opposite angles in any sort of parallelogram rhombus are always going to be equal. Okay, so we just finished up with rhombi, or rhombuses, So we're looking at now a special type of parallelogram, another one that you guys are familiar with, so hopefully it'll be easy, what's called a rectangle. So a rectangle, again, is a special type of quadrilateral, special type of parallelogram. A rhombus, like we just talked about, is a parallelogram where all 4 sides were equal. So a rectangle is a parallelogram where the opposite sides, or all four sides, are not equal. We do know from a parallelogram that the opposite sides are equal, so you can see here that A to B would be equal D to C, A to D would be equal B to C, but what makes a rectangle by definition is that all four of the angles in a rectangle are going to be 90 degrees, okay? So all four angles are going to be congruent. And again, what we do know is that with a four-sided object that all the angles should add up to 360 degrees. So if all four angles are the same or equal, if I were to divide 360 by 4, that means all of my angles would be equal to 90 degrees. So that is where that 90 degrees comes from, is because they're all the same. So what we're going to do is we're going to look at some special properties of rectangles. Obviously, you guys should know some of the basics of it, such as the opposite sides being equal, here all the angles being 90 degrees. You've been recognizing that we've been talking about the last two sections about diagonals. So diagonals of a rectangle here are going to be congruent to each other. So following the same ideas of parallelograms, we do know that they're going to bisect each other. So you'll see here that all four of these little chunks are going to be bisected, but since the diagonals are equal in length, that you'll see here that all of these little chunks, all the way to that midpoint there, they're all going to be equal. So nice, easy properties when we do with a rectangle. So just like we did with a rhombus, we're going to use this idea to try and solve for things. So in this first example, we have our rectangle QRST. It says here that Q to S is 5x minus 31, and R to T is 2x plus 11. So Q to S would be the diagonal that we see here, and then R to T would be the diagonal we see here. Now, knowing, again, within a rectangle that our diagonals are going to be the same, I can take the 5x minus 31, and I can set that equal to 2x plus 11. And again, I give myself a little equation that I can solve. So I'll go ahead and solve this one for you. All right, so what you should get, solving for x, I got x equals 14. You can follow the steps there. By plugging in 14, I'll get for Q to S. Q to S would be 39 for its total length. Plugging in 14 for R to T, I would get 39. So again, notice the diagonals are equal in length when I plug in that value for x. All right, next example, kind of digging a little bit deeper with rectangles, using some stuff you already know. It says here QRST is a rectangle. It says the length of the rectangle is 2 times larger than the width. It says here the perimeter of the rectangle is 48 inches, and I want to know what is the length and the width. All right, so this one is just not really related to diagonals, but using properties of rectangles. So again, if I had Q, R, S, and T here, says here that we have the length and the width. So think of the length of a rectangle as the longer side here. So this would be considered the length, and then the width would be the shorter of the two sides. So it says here that the rectangle's length is 2 times, so it's going to be 2 times larger than the width of the rectangle, I'm sorry. Okay, so what we can think about is this. Our goal is that we know that the perimeter is going to equal 48 inches. So if we remember what the perimeter is taken by the length and the width and the length and the width. If I take all four sides and add them up, I should get 48 inches. So again, it's going to be the length plus the width plus the length plus the width should give me 48. Now here's what we're told. We are told that the length is 2 times longer than the width. So the way I can set this up is that if the width, let's just say, is x, then I know that the length is going to be 2 times larger than that, so I can say, 2x. Hey, how about that? So if I plug this into my equation, I would have 2x, and then I would add to that the width, which is x, and then I would add to it again the length, which is going to be 2x, and then the width again, which would be x. All those things should add up to the total perimeter of 48. So what that means then, if I look here that I have all these x's, 2x plus 2x plus x, add those all together, you should get 6x equals 48. That's kind of nice. And then if I just divide, I don't know why I divide by 8, but I want to divide by 6, which would give me then x is 8. So that means I know that the width of this rectangle would be 8, and the length is going to be, in this case, 16. Now, is it always going to be that type of relationship? No. What we do got to know, though, is that, again, with a rectangle, just like all parallelograms, opposite sides are equal. So I know that all the widths and all the lengths would be 8. So again, this is just using properties of rectangles that you guys hopefully should already know at this point. All right, last special type of parallelogram is the easiest of all of them, a square. Okay, square is just what all you guys are. Just kidding there. Square is a special type parallelogram where it's kind of like a combination of a rhombus and a rectangle. It's where all four sides and all four angles are equal. So no matter what the side lengths are, you can have different sizes for the square. Could be big or small. All four sides are always going to be equal, and then all four angles, just like a rectangle, are going to be all 90 degrees. Okay, so a square is a special type of parallelogram, but it's kind of a combination of a rhombus and a rectangle. So that's the last special type of parallelogram that we have. All right, so now in these last two examples, what we're going to do is plot our 4 points, and I want to know what shape do we have. Are we going to have a rectangle, a rhombus, or a square? So I'll do this first one with you guys here. So example A, I'm going to plot my 4 points, A, B, C, and D. All right, so plotting those 4 points, A, B, C, and D, I get this shape. So first of all, I should recognize right away that this is not going to be a rectangle or a square. You might be asking why. It's not going to be a rectangle or a square because in order to be a rectangle and a square, all the angles need to be 90 degrees. And you will see here that the angles that I have here at D and B and at A and C, that they are not 90 degrees. You got 2 acute angles and 2 obtuse angles, which means this could possibly be a rhombus. Now, just to check if it is a rhombus means that all the sides are going to be equal. So just to kind of prove this, I'm going to look at all 4 sides, and to do this, I'm going to look at the slope. Okay, I'm going to compare the slope here. So from A to B, notice it's going to go up 2, and it would go right 8 boxes. So that means I would have a slope of 2 over 8. If I compare that, let's say, to the side across from it, I see the same thing from D to C. It goes up 2 and then over 8. So again, that's going to have the same slope. And then if I look at B to C, now this one's going a different direction, but from B to C, it would go, in this case, left. Whoopsie daisies here. It would go left 2 and down 8. So again, we're going to have a slope of, in this case, 8 over 2, and it's going to be kind of the same numbers, just flipped. And then the same thing here for A to D, I would get 8 over 2. Okay, now using the slope, you'll see that we have the same numbers going on. So what that means is all 4 sides are going to be equal in length. So this would indeed be a rhombus. All right, so what I want you guys to do is try this last example on your own using your ideas of rectangles, rhombuses, and squares. Plot those 4 points and see what sort of shape it would be. So pause the video, give this one a shot on your own. All right, so plotting those 4 points, I would get myself a nice, looks like a square. I can recognize right away that I have 4 90-degree angles, 4 right angles, so I know at least it's a rectangle. When you count the number of boxes then, what I did for all 4 sides, counting boxes, I got all 4 sides equal to 7. So this, in getting real specific, would be a square because all 4 sides are equal and all 4 angles are 90 degrees. So a lot of meat and potatoes again in this section, but we looked at rhombuses, rectangles, and squares, special types of parallelograms, and then related things like the diagonals and the angles in these different shapes. So again, if you have any questions, jot those things down. Good luck on the practice problems. Make sure to ask any questions you need as you go through.